Welcome to the 12th video of our 5th unit of AP Chem called Free Energy and the Equilibrium Constant. This is a very, very important unit video. Feel free to rewatch it if you're stuck, but let's go. So, while we often talk about determining delta G under standard conditions, we're often also interested when it's not standard. So here's an equation that can help us do this. This says that our delta G when we're not standard is equal to our standard plus this little kind of fluff factor, which is RT times natural log of Q. That is a plus. On the actual PowerPoint that I had, it was an equal sign, so I had to cross it out. But we're going to talk more about this equation and what those variables actually mean. So, yeah. Oh, keep in mind, that actual 0 means standard, just kind of reminding you. So, not standard, standard. So, delta G, that's your equation again. R is our gas constant of 8.314. This is the one we learned a while ago. I told you, remember the number, don't worry about the units, but now we actually care about our units being joules. Q is our reaction quotient, which is just determined the same way as K, but before we actually establish equilibrium. So, there you go. Now, at equilibrium, the above equation turns into this. In case you'd like to know, that's because at equilibrium, that's kind of how definition, if you ever find that your Gibbs changes 0, it's at equilibrium. So that will turn into a 0. We can solve for our standard G. And notice this is now a K. Now, here's where this all just starts getting kind of trippy. And you may or may not like this. I find it awesome. We can then arrange that equation to solve for K. Now, notice in this one equation, we have our equilibrium constant, our Gibbs free energy change, our gas constant, and our temperature, and E. That means we are relating in one equation, unit, let's see, 2. Let's see, we don't actually have kinetics in here, but kind of 3 is somewhat implied. Anyways, unit 2. Oh, we'll talk about temperature. There, 3, with 4, with 5. Almost everything you've learned in one equation. More specifically, this shows that when our standard G is negative, that means our K is actually greater than 1, which means that depending on our Gibbs energy change, we can get an idea of how our equilibrium constant means. Even without actually even seeing the equation, we can still find our equilibrium constant. I think that's awesome. You may not whatsoever, but I still find that really, really cool. So, sometimes, however, a process may be thermodynamically favored, like, again, spontaneous, but will not proceed at a measurable rate. So, this is actually due to a very high activation energy typically, and it's said to be under kinetic control. To be honest, this is just kind of random trivia that I've seen, I figured you may need. It kind of didn't really fit any better anywhere else, so just figured I'd tell you. Just because things are technically favored, that does not mean they're going to go fast. They may be spontaneous, but they may be very slow. That's okay. We call it under kinetic control. Again, kinetics referring to the rate of reaction. All right. So we are now going to find delta G at 298 Kelvin for a mixture of those gases at those pressures being used in the Haber process below, which is here. So I want you to pause the video and try it. And yes, I'm serious. You can figure this out. You have the information with you. I'm going to give you plenty of time, but you can learn on your own, despite what you may think. So give you some minutes. Come back in a bit. So to begin with, there's our equation. This is the work I got to find my standard Gibbs. I plugged in values using my Gibbs values at the back to that equation. That gave me information in kilojoules, though I need things in joules to make my life easier. So that is that value in joules. Okay, I'm going to now write RT, and then I'll show you how to get Q. Again, you should have an idea. If not, go ahead and pause the video and try and finish it from here. So there you go. Well, pause / keep waiting. All right. So here's the rest of my values. R we knew, T they told us, Q is just make your equilibrium constant plug in the values they gave us. That's our value of Q. Last check. You should be able to get the rest from here. So, pause it, make sure you've got this work, find the final answer. I'll have it up for you in just a bit. Alright, my final answer is negative 44.9 kilojoules. Plugged in those values to my equation. Okay, if you don't get this, rewatch it, look at your notes. You got to learn how to actually deal with equations on your own. So, it is a hard problem, but none of the steps take all that long. Hopefully you can do this. Alright, so we got one more equation, or one more example. Alright, first off, I forgot to give you the equation. There you go. So, secondly, go find this out. Again, pause, try it, come back in a bit, and I'll show you how to get the answer. Alright, so we're finding our equilibrium constant, which is K. Using delta G, that means we're going to have to use this equation, especially since they gave us our standard. Plugging in our values, keeping in mind that delta G was given in kilojoules, but we need joules. And also keeping in mind that this is all E to the power of, all that. That gets us 7.0 times 10 to the 5th. That's your answer. Hopefully you figured it out. If not, well, stare at it until you do. Thanks for watching, guys.